All right, so welcome back. So now in this second half of the tutorial, we will look at smooth maps and Lie and covariant derivatives. This is what I will now present in the first part, and then Markus will take the second part where he switches gear to Lie groups and Lie algebras, which are also very important constructs. So the idea of this first part that I'm presenting is that we are really interested in the Lie and the covariant derivative, which is two different kinds of derivatives on smooth manifolds, or I should say on Riemannian manifolds. And in order to understand them, we will first have to look into smooth maps, the definition of smooth maps. All right, so smooth maps basically take points from the manifold and map them to points of another manifold in the most general setting. There's a special case of that is diffeomorphisms that do that in a differentiable way. They're smooth, they're bijective, and they have a smooth inverse. So it's like a very nice class of smooth maps that we can use for a lot of useful constructions on the manifold. What this gives us, such a diffeomorphism, such a map from points to points, are two other constructs that are called the push forward and the pull back. And we will look at them in detail, what they mean, and we can use them for a lot of things. And in particular, we will use them to define derivatives on the manifold. So there's lots of applications of smooth maps, and there's lots of different kinds of smooth maps with applications in continuum mechanics, visualization, graphics. The maps that everyone knows are like transformations or deformations, and then there's what we also use a lot, reference frame transformations, where we change coordinate systems. So let's look at these smooth maps, and in particular at diffeomorphisms. We have a map that maps each point on a manifold. So this map is called phi t here, and it takes points from the manifold and maps them to points on another manifold. A very important subclass of that is the diffeomorphisms that map from the manifold to points of the same manifold. So we have a mapping between a manifold and itself, and we just map points. A smooth map eats a point and gives us a point. And in the general setting, it can be different manifolds, but we will mostly be looking at mappings that map on the same manifold again. So here is an illustration of this. We have a point, and we also have to consider the region around the point, because diffeomorphisms are mappings in differentiable ways. So, and this map, phi g, maps to a new point. There's really nothing special to this, but this diffeomorphism works on the whole manifold. So all the points are being mapped to all points on the manifold. And this now allows us also to map curves. And we have seen curves already as these constituent elements that will allow us to define vectors. So we can, by mapping curves, we'll later also see how to map vectors under this smooth map. This diffeomorphism always has also an inverse defined, which we will also need for certain constructions. Also very important is when we look at the diffeomorphism, it's really just one map from points of the manifold to points on the manifold. But very often we need not one map, but we need a whole family, a whole parameter group of maps. And then that parameter group depends on a parameter, for example, t, the time. And then we have, for each t, we have a different diffeomorphism. So a different mapping from manifold points to manifold points. But there's not one, but there's this whole parameter group. One important example from the literature is from this nice paper about visualization techniques is the flow map. And the flow map really is such a diffeomorphism parameter group. And it's basically, we can think of it as taking the integral of a vector field, like path line integration through the vector field. And then this map here, this f subscript t0 and superscript t would be the map from points at t0 to t, and we map by really following the flow of the path line. So that way we can map all the points on the manifold to new points. And then this allows us here, we have like some sample visualizations for 2 different time points. We see how such a texture that we can advect, for example, here, such a checkerboard texture, how this would evolve, and that gives us already quite a good understanding of what is happening here in this flow data. So we can see this flow map as the advection of the material coordinates. It's important to note that the flow map has a physical meaning that doesn't depend on the coordinates, but of course we can use it to do texture advection with using Cartesian coordinates. When we have such a diffeomorphism, then what we immediately can construct from it is what is called the push forward. We already said that these smooth maps, like the phi t, that maps just the points of the manifold. And now the push forward is the construction where we map vectors between tangent spaces on the manifold. So we can kind of transfer from one tangent space to another under this push forward that is defined implicitly with a diffeomorphism. So a diffeomorphism can map vector fields, it actually maps vectors between tangent spaces, but when we do this on the whole manifold, because the diffeomorphism is defined on the whole manifold, we can also map whole vector fields to new vector fields. So this is how we would write that. Here again we see the diffeomorphism phi t, and then the push forward would be d phi t. In this case, when we write it like this without a point, then it would have the meaning that we map the tangent bundle to the tangent bundle. So an entire vector field. Whereas here, where we explicitly write the point, this would really be just a mapping from txm, so the tangent space at point x, to a new tangent space that is at this different point, and this different point comes from the diffeomorphism, and we have a construction of a tangent space there. So we map an element, a vector, from this tangent space to another element of this other tangent space, and this is what is called the push forward. So the push forward works on vectors, but in general, more generally, we can also make it work on tensors. So we can map either tensors between tensor spaces or entire tensor bundles on the manifold. There's a very intuitive illustration for this, how this works. So we have seen this already. We take our diffeomorphism and we map from one point to another point, where we have the mapping is defined for a region around this point, which also allows us now to map curves. So we can map entire curves to other curves. And what the push forward does is it maps from this one tangent space on the left to the tangent space on the right that lives somewhere completely different on the manifold. But by just mapping, by just taking the tangent of this curve that we can map, we obviously can also use this map, the push forward, to get a tangent of the other curve, and this is what is called the push forward. So it's a linear map between these tangent spaces. And also always the inverse exists, so we can, for some mathematical constructions, we will need also the inverse of this. Again, there's an example from the same paper here, where what is called the flow map gradient. So this would be here this nabla f, where basically this here describes a mapping between these tangent spaces that is valid for Cartesian coordinates. And here this nabla here is very common to be used for the gradient, but we will later see that this nabla actually has the meaning of the covariant derivative and is in general possible to do this on curved manifolds also. The construction would be different. And here we could also reformulate basically this flow map gradient just as the push forward of the flow map. So it's really a mapping between these tangent bundles. There's another construction, that's the pullback, that is very similar in a sense. It also maps from one tangent space to another tangent space, or actually I should say from a one-form space to a one-form space. So in the first session we have seen what one-forms are, and now we also can define mappings for these one-forms that directly follow from diffeomorphism. Actually, there's more to it. There's a lot more detail that the pullback and also the push forward can be also defined not only from diffeomorphisms, but it's a more general concept, but then there's restrictions. So a lot of the details is in the tutorial course notes that you can find on our webpage. We will skip all these details here, and we will only be concerned with pullbacks that are defined on diffeomorphisms. And what happens is it's very, I would say, quite intuitively defined, such a push forward, by taking a vector as an input and mapping this vector via our push forward to a new vector in a different tangent space, and then evaluating the one form in this new tangent space. So this here would be the one form. And this new one form here is the definition of the pullback at our original tangent space. So this is also a one form. We also evaluate the vector. And this is kind of the recipe how we evaluate it, by first pushing forward the vector, transferring it from one tangent space to another one. Defined is this push forward by this diffeomorphism here. And then we just evaluate the one form over there, which gives us a result that we kind of pulled back the one form to the original point. Again, we have an illustration here. We're kind of reusing this illustration because it makes things a lot easier. So we have this construction here with the tangent spaces. And now we take a vector from this tangent space here, this vector. We transfer it over here using the push forward that follows from that is given by the diffeomorphism, basically. And then we can use this vector over here to evaluate the one form, the differential one form that is given on the manifold. So this would be the push forward of the vector. It's just this vector here. We evaluate the one form, which gives us a scalar. And transferring a scalar between spaces is very simple because we don't have to do anything. It's just the scalar. So it would give us the result of the one form in this original tangent space, or at this original point. Okay, so why are we looking at these smooth maps and these push forwards and pullbacks? This is because we will need them now to define the Lie and the covariant derivative. So derivatives can be kind of intimidating, I guess, and then there's also this thing that there's not one derivative, but many. And now we will look into these very two important derivatives, and we will look a bit into what are the commonalities, how are they different, and also, most importantly, how are they constructed. So what does it give us, the Lie derivative and the covariant derivative? It basically tells us how a certain field changes at a point x in a given direction u. So we have any kind of field. That field can be a scalar field, that field can be a vector field, it can be a differential form, or it can be a tensor. So actually it would be enough if I said it can be a tensor, because all of the others are just examples of tensor fields. But kind of intuition-wise, it's easier to think about scalar fields, vector fields, and one-form fields. But in general, they can do tensors. And they will evaluate, or we want them to give us the change, how that field W changes in the direction U. Okay, so let's look at the equation first of the Lie derivative. And as I said, can be a bit intimidating because there's lots of different symbols and lots of different constructs. But I will now really take the time and break that down to the elementary parts that I think it's understandable what is going on here. So we'll start just with this notation here on the right. This is the Lie derivative at a point x. And we take the derivative in the direction u. So this is by convention just how it's written, the Lie derivative in direction u. And now I have to tell of what I'm taking the derivative. I'm taking it in general of a tensor field. So the whole thing, the Lie derivative, will again evaluate in a tensor field. And now the question is how we're doing this. Well, I mean, derivatives, we know that from like simple calculus, how they are typically constructed. And this is constructed the same way, basically. So what we are doing is we are taking two elements of the tensor field, one at the point x and one at a slightly different point. And we will have to say something about which other point we are taking here. Somehow this point needs to depend on the t, because it's like some point in the neighborhood that is with a parameter t. We can kind of shift it, and we will see how we'll do it. And then we divide by t, and we take the limit case of t. So as t goes to 0, will give us the directional or the derivative of this tensor field. Okay, so there's a couple of things here missing, and it mostly is has to do with that we really don't know like which point are we talking about here, right? We're talking about a general manifold, so we somehow need to construct this other point. And as it stands here at the moment, we cannot do this subtraction even, because clearly this tensor here lives at a different point than this tensor. So we cannot just make subtraction because they are elements of two entirely different spaces. So the solution to this is what we have already seen. We use a map, we use a smooth map that takes us from the point X to another point, and then from this smooth map we can define the push forward. So we will be able to transfer this vector, this tensor here to the other tensor space, to our original tensor space, and then we have a nicely defined subtraction here. And then we can divide by t, and we can take the limit. So this is how the Lie derivative is constructed. I still have to talk about these two question marks here, obviously. I mean, they're not really, that's nothing you want to see in an equation, right? But the idea is already clear that we are now taking two tensors from two different tensor spaces. We are transferring the one tensor to the other tensor space at the point X, and then we subtract them, and in the limit case, this is exactly what gives us the derivative. So let's talk about this question mark here briefly. Actually, what we're doing is, so I call this here the push forward already, but what we need is not the push forward, but the inverse of the push forward. So we need to kind of get from the other vector space, we need to get the vector R, the tensor. So we need here what we need is the inverse of the push forward. Okay, illustration-wise, this is how it looks. We have our two different tangent spaces. This could now be also tensor spaces, but like to keep it simple, we do the illustration with vectors. So what we do, this is just a repetition of, we just can like get this vector here from the other tangent space back to our original tensor space by using the inverse of the push forward. All right, so we can now replace our question marks here with, because we know what they are now, we have to construct a diffeomorphism that depends on t, and then we can use afterwards the inverse of the push forward to evaluate that. So the only missing piece of the puzzle is how do we construct here this smooth map? And this is where the definition of the Lie derivative comes in. So there was Sophus Lie who like solved this puzzle, how can we do this? And he defines basically this map just as a curve that goes along U. So we have an input vector field, and that's important here for the Lie derivative, we need an input vector field U. And we take curves along this vector field to define this diffeomorphism. And once we have the diffeomorphism, the rest is clear. There follows a push forward, there follows an inverse push forward, so we can suddenly do the subtraction here, we can divide by t, and we can do the limit case when t goes to 0. And this is exactly the definition of the Lie derivative. Okay, so I will show a short animation in a second that maybe makes this a bit more clear or gives some more intuition maybe. But the important takeaway is here that we somehow need to connect neighboring tensor spaces. And the Lie derivative has a very special way of making this connection between the tensor spaces. It just uses the vector field U. And then I can only evaluate the directional derivative in the direction of U. So that's kind of a limitation, but that's what the Lie derivative does. It gives you the directional derivative in the direction of U. So we kind of use the flow map, if you want to call it that. We make integral curves of U, and these are the curves think about it. What we have seen in the first session, we're coming back to this coordinate maps. So depending on the definition of coordinate maps that give you or the chart maps that give you a chart-induced basis here, we can basically think of how we advect this vector or how we push forward this vector. We can also think of it as pushing forward the basis vectors and then just doing linear combinations of this. So it's the same computation that you can do is basically pushing forward the basis vectors and then using the linear combination of them to evaluate that for a vector. All right, so this is the Lie derivative. I hope you could follow that how it's constructed. Very important is that we understand that the Lie derivative takes a whole vector field u as input, and this gives us the directions in which we evaluate the derivative. It only evaluates in this direction of u at each point. Another construction of a derivative is the covariant derivative that actually can evaluate derivatives at every point in every direction. And for this to work, we need some additional structure on the manifold, and this structure is called the connection. And the connection is really just, it's an additional thing that we have to choose, and we have to somehow describe it on the manifold. Without this connection, we don't know how neighboring tangent spaces are connected. And now, if we have a connection, and we will talk a bit about that in a second, how such a connection would look like. Once we have a connection, then we can suddenly evaluate our directional derivative in any direction at any point. So this is the difference to the Lie derivative. So a connection is really the meaning of connection is how are neighboring tangent spaces connected with each other. How can I, and that will allow us to do a directional derivative that is called the covariant derivative. Works again for tensor fields in general, but also this connection gives rise to a lot more other constructs also. Like it also answers the questions in two different tangent spaces, which vectors are parallel. The notion of parallel is very intuitive to us because we typically think in Euclidean spaces, and then that's very obvious what we mean with parallel. But if we think of vectors on the sphere, for example, it's not obvious at all what we mean by parallel, right? I mean, it's two vectors in different tangent spaces. They don't have anything in common until we endow our manifold with something like a connection, where we can really use the connection then to transport vectors, and which is called the parallel transport. And then we can start comparing vectors. I should say this is not completely that simple because the parallel transport depends also on the curve. So if I parallelly transport a vector from one point to another point, there is not one solution that I will get, but it actually also depends on the curve. So what we will use this for is again just in the infinitesimal sense, this parallel transport, because like it tells us what means parallel in a direction that I'm going. And this gives also raises the definition of a geodesic. A geodesic is kind of a straight line, but straight on a curved manifold is not really straight, but it's like the shortest path on the manifold, and that is we can construct from this notion of the parallel transport. As I already said, the connection is not unique. It's an additional structure on the manifold that we have to define, and there's a choice that we can make for different connections. Here, I will talk about this choice a little bit later. Now I want to give the definition first of the covariant derivative. That was kind of the goal, to define it, and it's very similar to how we defined the Lie derivative. So we have a new notation, of course, because it's not the same. So we have this covariant derivative of in the direction u. Now u is not a vector field, but it can be any vector at any point. So we again start at a point. We have a tensor field that would be our w here. We are evaluating at a point x, and we are evaluating in the direction of a vector u. Again, the result will be a tensor field of the same order, of the same type of tensor. And we construct it very similar to the Lie derivative. So we again need to compare two elements of two different tensor spaces, the one at the point x and the other one somewhere close by. And this close by, again, we need to kind of define what it means in a second. That's why we have a question mark here. And then we subtract the two divide by t, and take the limit as t goes to 0. And this gives us the covariant derivative. So again, we have to say something about how now these things are defined. So somehow we need this parameter group, this diffeomorphism group with the parameter t now. And we need again something that connects the neighboring tensor spaces. We cannot simply do the subtraction because these elements are in different tensor spaces. So we have to transfer the one back to the original tensor space at point x. And now this is constructed a little bit different than with the Lie derivative. Basically, it's very simple here. The diffeomorphism group is just a curve that goes in the direction of u. So we have a vector and we already have a tangent. So we have a curve that goes in the direction of the vector. And we can just use this to define the diffeomorphism. And then we have this new structure that can tell us in any direction where we're going, how do we transfer them between tensor spaces. And this is called the connection. And it allows us to like parallelly transport one vector between two vector spaces, or in more general, one tensor to a new tensor space. So it's very similar to the Lie derivative, but we are replacing this vector field u with a more general thing that can be a curve in any direction u. And then we use the parallel transport that comes from the connection that we know how to compute it to transfer tensors between the tensor spaces. All right, so I think I said that already. It's quite similar. They both have the meaning of a directional derivative. Both work on tensor fields. The difference is that the covariant derivative works in all directions at a point, and it uses the parallel transport instead of the Lie dragging. So now we have to say something more about this additional structure that we need, this connection, how we do the transfer between tensor spaces. And there is a special connection, so there's no unique connection in general on manifolds, and also not on Riemannian manifolds. But when we do have a Riemannian manifold, the thing that we have already is the metric. And there's one special connection that is that we can uniquely identify, and that's called the Levi-Civita connection. That's very often used when you have a Riemannian manifold. You can say, well, then also I have a Levi-Civita connection, and that has certain properties that are often desirable. And the properties are that it's torsion-free. So here we have here we have a definition of what the torsion is. So the torsion is the covariant derivative in the direction of. So okay, torsion is for any two vector fields basically. So I have two vector fields x and y, and I can now evaluate the torsion that's defined as this here, which is the covariant derivative of the one vector field in the direction of the other one minus the exact opposite. And then when this is the same as the Lie derivative, then this whole term will evaluate to 0, and that means that it's torsion-free. So this is just the torsion here. This is the definition of the torsion, and this Levi-Civita connection is the unique connection that when I have a metric already fulfills this property. The other property it fulfills is it preserves the metric. And when we say it preserves the metric, that really means we have seen in the first session today that when we have a metric tensor, the metric tensor G, we can take the derivatives of this metric tensor G, and if that is 0 everywhere, then the metric doesn't change basically. Or it's preserved by this derivative. Also, this Levi-Civita connection has a very nice property. It is what would match our intuition, how we would connect tangent spaces on a Euclidean manifold. Like if you think of the sphere, then it would match with how neighboring tangent spaces are connected by basically by embedding that in this higher dimensional space. So our two sphere we could embed into the space R3, and then this connection, this particular connection here, has the property that the neighboring tangent spaces are connected as kind of how we would expect it. Well, okay, that's a bit hard to define. But you have like a better intuition. So this is the kind of the intuitive connection when you have a metric. Okay, there's a little bit that I have to say about notation, because this covariant derivative is used a lot, and it's used in a lot of context, and by the context, the notation changes slightly and the meaning changes. So when you try to parse equations, then this is one of the obstacles often to understand the equation itself, because there's so many different constructions that come from this covariant derivative, because it's so important that we have to kind of infer the meaning of this particular instance of how it's done. So this here now is the covariant derivative that we have looked at, that we should have an understanding now. It's the derivative at a point x in direction u of the tensor field w. And now from this, I mean, kind of there's a lot of abuse of notation, or I mean, some of it is abuse, others are real constructs that make sense. But anyways, there's a lot of things that can be done with this here. So first of all, we have already said that I can just leave away the x, and then this is now the covariant derivative, not anymore of a tensor, but of a tensor field. So I can also do the covariant derivative of a whole tensor field. Of course, now I need, as u, I need again a vector field. So in general, the covariant derivative just works in any direction u at a point that is just a vector. But if I have a vector field and I want the covariant derivative, I can do the covariant derivative along this whole vector field. And then I get another tensor field. Then there's this other notation here, where I simply leave away this field. So now I have this strange thing left here, which is a directional derivative in the direction of a vector field u, but I leave away of what I will take the derivative. And this is not a tensor. This is really just like it's an operator. So it doesn't follow the definition of a tensor, but I can kind of conveniently use it in the obvious way that, well, it's kind of missing the field. So when I plug in the field, then it is again a tensor field. So it gives me the derivative of this tensor field. Then there's another notation, and this notation is exactly the same as this one here. So the meaning of it is exactly the same, but sometimes this notation is preferable, and I will give a reason in a second. So, but the meaning here is really, again, the covariant derivative of the tensor field in the direction of the vector field u. Exactly what we have seen here. It's the same tensor field. Why have we changed this notation? Well, the reason is because now we can leave away the u, we can leave away the direction, and we can write this nabla w, which we can use, or is useful in many contexts. So by leaving away this u, by leaving away the direction, we go from a tensor field of order nm, so this here would evaluate to a tensor field of order nm. We suddenly go to a tensor field of order n plus 1. So we have seen this, that tensors are defined by the input arguments, basically, or their type is defined by the input arguments, so that when I now leave away the direction, the vector, then I have a new tensor, this nabla w, but I need to kind of feed it an additional vector now. So I constructed from this one tensor field, I constructed another one of a different type, and this is often very useful. So of course we can now leave away also this brackets, the empty brackets here. So this here would now be another tensor field, and this tensor field has a different order than the input tensor field w. Okay, so I think this is important because this can be very hard when you read through texts and different equations. All of these different combinations kind of show up, and it takes a lot of time to like go back and think of, what is this now? Is this now a tensor? Is it a tensor field? Is it a tensor field of a different type? Or is it just an operator, a differential operator? They look all very similar. It kind of, when you think about it, that this is the one kind of most general definition, then you cannot infer the meaning of the other ones by, well, okay, I left away this one, so obviously this must be a tensor of different form. You can kind of do this, these notational tricks and learn how to interpret them. Okay, so we will now do an important example of such a covariant derivative, and that's the velocity gradient tensor. So we start with a vector field. So our input tensor field is a tensor of type is a tensor field of type 1, 0, which means so it's just a very special case, basically, of a tensor field, right? We want to take the directional derivative of a vector field. Of course, very useful. So the directional derivative here, using the covariant derivative, and now I use this notation here, where I say I want to take the directional derivative of V, could be a tensor field, but simple case now, vector field, and I take it in the direction of U, and then this directional derivative is the this is just a covariant derivative, basically, and from this I can construct what is called the velocity gradient tensor, basically by just leaving away this U. As we have just said it on the last slide, we leave away this, so that gives us a new tensor field of a type 1, 1, so it's one tensor, one vector and one form as input, and we construct this by leaving away this U, so we need an additional vector here to evaluate this velocity gradient tensor. I will now show, so far we have talked a lot about these general concepts that have geometric meaning and that are completely independent of coordinate systems. I will now do one example where I walk through where we take now this velocity gradient tensor and we actually refer it to a choice of coordinates. So we always said, like, once we choose the coordinates, kind of everything else follows, and I will now do an example here of how this velocity gradient tensor is defined in terms of coordinates, and how the equations that we get from this are different for different coordinate systems. So in practice, what you have is this, when we talk about coordinates, we actually can think of it as a 2x2 matrix here. So later we can feed it a vector, and we would do a vector matrix multiplication. So somehow we need to define 4 numbers, right? So when we choose a coordinate system, then immediately from the choice of coordinate system, 4 numbers should follow. There must be a recipe that tells us these 4 numbers. And this recipe is basically, yeah, we give these 4 components, we give them different names with in tensor notation with different indices. And we have one equation that really tells us for each of these elements how do I compute it. So again, there's now symbols that we need to talk about, what they mean and what they are. But this equation is the correct equation in tensor notation for each of these symbols, no matter what your choice of coordinate system is. Once you choose your coordinate system, this will be evaluated to different numbers, meaning that these will be different numbers. But this is the general equation that works for any coordinate system. Okay, so let's do an example for we want to find out this one element of our matrix here. What we do is we just fill in basically the indices into our general equation. So we can put the 1s in place first, and then we put the 2 in place first, second, and then we have the k left. So we just leave the k for now open. And then we need to understand the meaning of these symbols here, but that's all that has to be said, how to figure out this one number here. Okay, so let's look at the individual symbols. So we have here, this is something that we really know how to compute it. We just take the first component of the vector field, that's V superscript 1, that's the first component, so we can think of this as a scalar field. And then we take the partial derivative with respect to the second coordinate function. So this is something that we should be familiar with. It's a partial derivative. It's something we are used to how to compute it in Cartesian coordinates, or so it's like elementary calculus, basically. And then we have here these strange-looking symbols that are called the Christoffel symbols, and we have to take a sum of them between this k. This is the Einstein summation convention here again. How do we look time-wise? Tight? Okay. All right. I mean, all these details are in the tutorial notes. There's also online videos where I do this. You can watch that if you're really interested in this construction. what I wanted to say, okay, briefly speed this up here. So basically you have to use these Christoffel symbols, and these Christoffel symbols, we can actually get them as vector fields of the basis vector fields. So these are just the directional derivatives of the vector fields, of the different basis vector fields. Okay, there's a lot more to be said about this. I guess I don't have time. The main point, the takeaway here is that when we do this construction, this evaluates all to something that is very simple, and then we know how to evaluate to such a matrix. And the matrix is the thing that when I have chosen my coordinates, is the thing that I can use to compute with vectors that use the same coordinate system. If I now do this construction for Cartesian coordinates, then this velocity gradient tensor simplifies to something very simple. It's just these partial derivatives of the different components. So it's just this term. The other term gets cancelled out because for Cartesian coordinates, these are all zero. These Christoffel symbols are zero. So we really just have the first term left. And this is like a very familiar looking object to many people. This is just the velocity gradient tensor in Cartesian coordinates. When we do this in other coordinate system, can be polar coordinates or it could be any other choice of coordinate system, then these symbols are not zero anymore. So this is really what the connection is that gives us the encoding that we need. Difficult case. Sorry, not more details here. I'm at the end of my time, and this is also the end of my presentation. Who will do Lie derivatives and, no, sorry, Lie groups and Lie algebras, I guess, and applications.
Okay, thank you very much, Peter. So I'll continue from this smooth map part. So first explain how we would now characterize isometries, and that is very much related to Lie groups and Lie algebras. And at the end, if we have time, we'll look a little bit at how we use that for observable reference frame relative computations. So Peter showed this basic pullback construction. So for diffeomorphisms, it's actually very easy. We can do the pullback or the push forward. It just depends on in which direction it goes. For non-diffeomorphisms, there's different characteristics what the pullback can do and what the push forward can do. But in the end here, it's now basically very similar. But a very nice example that we can look at is what's called the pullback metric. So basically, we transfer this metric tensor field from one manifold to another manifold. So here the manifold that we want to transfer from is the right one, so it's the manifold N, and the manifold that we want to transfer to is the left manifold, it's the manifold M. And so we have now a metric tensor field given here. It's not called G because we need two, so it's not always called G, we can also call it H. So this is the metric tensor field on this manifold. And then we want to now basically transfer this tensor field to our original manifold. So we have a diffeomorphism phi here. So for every point x, we go to phi of x, and then we want to kind of transfer the metric tensor from there. And this is what's called the pullback metric. So basically, we pull the tensor field back from the target manifold to some source manifold. This is just a very general construction, and if we then have two metrics equivalent on the manifold M and on the manifold N, this is how we define an isometry, for example. But in principle, we can just say we start here at any point x, we go here, we do the push forward. So basically, we would evaluate the tensor field H by using two vectors, but the vectors now come from here in the tangent space here. They're pushed forward to the right side. So these are the pushed forward version of the two vectors. And then we evaluate, in this case, the metric tensor field H here. And this gives us a scalar, and this is just what is defined to be the result of the inner product between these two vectors on this side. So it basically connects the two manifolds. and lets us evaluate the metric tensor here without being given a metric tensor because we pulled it from here. But of course, then that evaluates to a new metric here, which is called the pullback of the metric H, which is phi star H. So basically, we can write this in inner product notation or in tensor notation. It just means that we define an inner product on the left manifold M by just transferring or pulling back the inner product on the manifold N. So now we could have a different metric on this manifold. So now it's called G. So we have now a metric G here. We had a metric H here. We pulled it back to the metric that's phi star H. Now we can compare these two. And basically, they could match or they could not match. So in general, they're just very different. But if they do match, then we would say these two metrics match under this diffeomorphism, and then this diffeomorphism is called an isometry. So basically, isometry means we have a connection between two manifolds in the sense of having a diffeomorphism between the two, and then if the two metrics match, so that the given metric here matches the pullback metric, then it's an isometry. So it's just that the inner product is the same. And so this is also connected kind of to saying that a manifold is like an abstract construct, and when do we say when are they actually the same? Well, they are the same if the metric is the same in the sense of having a Riemannian manifold. Okay, so what we could also do is we could, for example, check for any diffeomorphism if now this diffeomorphism is isometry, but just checking if the pullback metric is the same as the original metric. So one example where something like this could be used is this here. So we can transfer these metrics through the diffeomorphism. And so there's this paper here that had the idea to say, well, can we not take feature detection approaches from one space where we have translations that are easy to characterize, but we want to transfer that to rotations. And then we can say, well, how does that connect to the metric? So the original paper did not do that with the metric, but we will now use it as an example for transferring the metric. So basically, the idea is that in a polar coordinate system, kind of rotations look somehow like translations in Cartesian space if you just take the coordinate space. And so we connect the two manifolds. In this case, in the end, it will be the same manifold. So we go from the left side with the diffeomorphism to the right side. The diffeomorphism is constructed just that it kind of rectifies a polar coordinate system into a Cartesian coordinate system. Then here we have a metric H, which is now the Euclidean metric here. And then we just pull it back to the left side, which gives us a new metric at this position. The interesting thing is now this is not a Euclidean metric because it's the pullback of the Euclidean metric under this diffeomorphism. That is not an isometry because the two coordinate systems don't match. So basically there's no physical meaning to the coordinate system. But if we deform a manifold under this coordinate system change, it will just deform, and this deformation of course changes the metric. Now if we have the metric, like Peter explained, the metric can be used to compute immediately a connection that's uniquely defined, this Levi-Civita connection. We take it from here and transfer it to here. Basically, we can say now the velocity gradient, or here in this paper, it's the Jacobian matrix that is updated, but basically it uses a different connection. So ultimately, it means it uses a different metric. So there's a new metric here, which we call, I don't know, a polar coordinate metric or something, but it's a different metric that's not Euclidean. But then we have from this the connection. That means we have the directional derivatives. And so now we know what the directional derivatives in this new space will be. Interesting here is it's all flat spaces, but still the metric is not Euclidean in the one space. So non-Euclidean doesn't necessarily mean it's curved. It just means that the definition of what angles and vector lengths are is just different between the two different spaces. So now basically we have Christoffel symbols that are non-zero, like Peter showed. That corresponds to a metric that is not Euclidean. But in this case, now we can do everything that in flow visualization is done within the velocity gradient tensor, and we just do it with a different connection, but it's not the Euclidean connection. And we basically can construct this exactly doing this pullback metric construction. But that entails then everything that directional derivatives do, so this covariant derivative, and it means that now these vectors count as parallel, because in this direction of this coordinate curve, the covariant derivative will be zero. So this is the new parallel transport. So parallel transport here is not Euclidean, but these vectors are parallel now. And also these vectors are parallel, which also entails that they have the same length. Well, if you check also the length. So that basically in the metric here, that would mean that these vectors count as the same length. But then ultimately we can do some changes, as was done in the original paper, to kind of transfer the meaning of rotations to translations. What we can also do, so basically we'll show some examples of what we can do with these pullback constructions. We can pull back vector fields. I mean, as I said before, for a diffeomorphism, it's just a matter of taste if you use the pullback or the push forward. For non-diffeomorphism, it's different. But we can, for example, reformulate what's the simple velocity transformation law. So that's related to observer relative computations. So if you have a reference frame or an observer that looks at some fluid flow, how would we transform the velocity vector field from one observer to another observer? And this is the typical, well, actually not, so it's a more complicated way to define this, how it's typically done, but we can just push this into this pullback construct, and then you just say the observed velocity, V star here, is just the pullback of the relative velocity field. So we have a velocity, that's the input velocity, we have a velocity that actually describes how the observer or the reference frame is moving, and then we can very briefly write this velocity transformation like this. And then we can do additional things like comparing this transformation law to other transformation laws. So on the next slide, we'll see what's a transformation of an objective vector field, which looks slightly different, but it's not the same. So that means that a velocity vector field is not objective. You can derive that in a more complicated way, but basically you can rewrite this as an operator that just see directly if it's objective or not. So here, this would be how a velocity field V transfers from one observer to another observer. Which could mean that a rotating motion is transformed into an observer that sees this as a non-rotating motion and so on. So we can use this to generalize objectivity. So objectivity is a concept that says, if I compute something, does it depend on the reference frame or not? And in general, we would like things to be not dependent on the reference frame. So if that is the case, we can say, when is a vector field objective? A vector field F is objective if it transfers from one observer or transforms from one observer to another one exactly with this rule. So it's just a pullback again. So we pull back any vector field F to a pulled back vector field F star. And if these two vector fields are just connected like this, then it's objective. If you go back one slide, this is not just a pullback of V. So the rule here is not V star equals pullback of V, but it's V star equals pullback of V minus W. And then in the end, the two rules don't match. So we immediately see that this is not an objective transformation, which means the velocity field is not objective. There are many ways how to see this, but I think in this formalism it's actually very, very easy to see. So this is for velocity fields or vector fields, and we can also do that for any other tensor field of any other order. Of course, very important would be second order tensor fields. In this case, one's covariant, one's contravariant, for example, the velocity gradient tensor that we have just seen. Then we could ask, is this velocity gradient tensor objective or not? We could compare the two transformation laws. Again, do they match? If they match, it's objective. If they don't match, it's not objective. So the next part, which is the main part of my talk now, is how this all connects to what's called Lie theory or Lie groups and Lie algebras. So basically, a Lie group is a group, like the typical mathematical group construction of an abstract group, but here it's a continuous group with a smooth group operation. And this group is not only a group like the permutation group or so, like a discrete group, but it's also a manifold. So a simple example would be all the two-dimensional rotations, which are usually drawn as a circle. So the circle would be the group, because every rotation angle is 1 point on the circle. So these groups are typically non-linear groups, so like a manifold like this. But we can again do the same construction that we did before in differential geometry. At any point on the manifold, we can take the tangent space. And this tangent space is what's called the Lie algebra. So there's always a notation for the group, let's say the special orthogonal group in 2D. That's just the rotations in 2D. And the corresponding tangent space is usually with this Fraktur notation here. And this is a linear space, so it's a vector space, and this is a non-linear manifold. So why is this called a Lie algebra? Basically, a vector space just has scalar multiplication, vector addition, but here we also added an additional product operation. This turns the vector space into an algebra, and this product is then called the Lie bracket. So we saw this Lie bracket before, the Lie bracket between two vector fields. It's actually the Lie derivative between these two vector fields. In this case, it's exactly the same. But here it basically just says what is an operation between between two algebra elements, and this is defined with the Lie bracket. So simple examples would be what everybody knows from computer graphics probably here. So this is the translation group, this is the rotation group, all in 2D, and this is all the translations and rotations. So this would be the group elements, and the derivatives we'll see on the next slides. So, but the important thing is like let's say a rotation is a Lie group element of the rotation group, and the derivative of a rotation, which then would often be called an infinitesimal rotation, is just the corresponding tangent space element, which is infinitesimal rotation, so that the derivative of a rotation. Since a Lie group is not linear, it's a bit hard to draw. So for example, this is all the 3D rotations, the special orthogonal group in 3D. So special just means that reflections are excluded. So this is kind of equivalent to all orthogonal matrices of positive determinant 1. If you would remove the S, it would also include of determinant -1, so include just mirroring. So here we have basically, it's a subspace of all the 3x3 matrices, but it's just only the subspace that corresponds to all the rotation matrices. And so we view this manifold, that's the Lie group, and then at the identity element, so I skipped over this, so basically we look only at the tangent space at the identity element, which for matrix groups would be the identity matrix. We take the derivative and we can really think about the manifold again like before and take a derivative here, and then this tangent vector is basically in this case an infinitesimal rotation. And we can look at a smooth path or a curve through all of the different rotations, which in this case would be all the rotations around one axis, for example. So if we then look at how many, well, what's the dimensionality of the manifold for all the 3D rotations, it's three-dimensional. That also means the tangent space is three-dimensional. So we need 3 basis vectors, in this case, to represent all the infinitesimal rotations. And so all of them would look like this. And we can derive that there's a one-to-one correspondence between all these derivatives of rotations in 3D and the antisymmetric matrices. So antisymmetric means just if I look at these elements, the sign flips if I mirror across the diagonal. And here's again the notation for the Lie bracket. So this is what completes the vector space. That's the tangent space here. Into Lie algebra, it needs this additional Lie bracket operation. So there's a lot more detail in the course notes. We skipped over all of that. I just would like to show some actual nice, I think, applications in flow visualization. So all of these transformation groups, including rotation groups, translation groups, and so is a very typical thing. But usually you look at it in the, let's say, computer graphic style also in terms of matrices, but we will now switch from matrices to vector fields. And we can construct isomorphisms between the two, so a one-to-one correspondence where we know which vector field corresponds to what matrix. But for some applications, especially in flow visualization where we're dealing with vector fields anyway, I think it's actually easier to look at the vector fields instead of the matrices. So the matrices have some confusing parts. On the one hand, it's easier to work with matrices. On the other hand, if you have a rotation, you have the problem, what's the center point around which you're rotating? So basically, if you're given a rotation matrix by itself, you don't even know what the rotation is because you don't know the origin of the rotation. If we do it with vector fields, there is no question about the origin of the rotation because it is just a vector field. Whatever the vector field is rotating around, this is what it's rotating around. With the matrices, it can be done exactly the same way, but there's basically some information missing. And that sometimes I think also causes some problems when this is used. Sure, for many applications the matrix is simpler, but I think in flow visualization it has actual advantages to look at the vector fields. So what can we do now? So we look at reference frame transformation. So basically a reference frame is like a rigid motion, so it's rigidly moving in space. Then it depends on what does that mean in what space. So that's also why we covered isometry. So basically rigid motion means isometric motion, so length and distances and so on stay the same, which we saw before as the inner product staying the same. But now we want to look at vector fields that describe rigid motions. So in this case in 2D, so vector fields that do rigid motion 2D can look like this. It's not all of them look like this. It could be translations and rotations. So this basically have both components, but also a rotational part. But now we can look at what does this map to in terms of this Lie algebra, and we can actually construct a Lie algebra of vector fields. So now we have a vector space, but every vector is more like a mathematical object that fulfills the definition of a vector space, a mathematical vector space. But now the vector is actually a vector field. So we say we have a basis vector, but this whole thing here, this whole field is a basis vector. In the terms of the vector space construction, it's a basis vector. In terms of what it really does on a manifold, it is a whole vector field that at every point gives us a vector. So it's completely different kinds of vectors, right? Like the abstract vector space construction is just a vector is an object that fulfills the following properties, and these vector fields do fulfill these properties. So we can now say all the rigid motions are actually forming the Lie algebra, a three-dimensional Lie algebra, and we can just pick three independent, linearly independent basis vectors, but in this case it's basis vector fields. So we have the first one, the second one, and the third one. It's not so hard to see here why they are linearly independent, but let's just assume they're linearly independent. And so we do a linear combination. It's three-dimensional, three basis vectors. So it's A, the first coefficient, times the first basis vector field, plus the second coefficient, times the second one, and so on. So any vector field like this, any rigid motion in 3D, in 2D, sorry, can be projected into these basis vectors. You might notice what looks kind of weird in the beginning. We are talking about 2D, but now the vector space is a 3D. Well, this is because it's the vector space, that's the Lie algebra of all the motions in 2D, but they have 3 degrees of freedom. It's 2 translational degrees of freedom and 1 rotational degree of freedom. But I think in the end, this construction makes it very easy. You just have to get around this notion that my basis vector is now a whole basis vector field, and then I do linear combinations. Linear combinations just means it's a constant A times the whole field. So of course, you're not allowed to multiply different points of this vector field with different A. So it has to be the same value of A. We can then immediately do this for time-dependent vector fields, so time-dependent rigid motions, by just having 3 coefficients per time step, and this just means we have time-dependent coefficients functions. We can then say what's now the time derivative of this vector field. Well, we just apply the time derivative operator, and then we have the fact that now we chose on purpose a basis vector fields that are time independent, so basically the time derivative is 0. So we would do the product rule and so on, but in the end we just say, well, we have the time derivative of this coefficient function plus the previous basis vector field. So it doesn't really matter what we do here. We just can take the same basis and just different coefficients, but in this case the coefficients give us the motion itself, and in this case if we take the time derivative of the coefficients, they give us the time derivative of the motion. So using a vector field does not make it much more complicated, but actually I think it can help avoid some mistakes in computation or simplify the computation after we got over this step that now it's kind of weird that we use vector fields. So time derivatives are really just straightforward. They are again a linear combination of the basis vector fields. We can also look at alternative bases if we like to. What's also interesting is that I guess this one here is obvious that this is kind of one part of the translation, this is another part of the translation, rotation is kind of in here. But this is exactly a basis for all of the translations and rotations. You just don't see it directly. These 3 vector fields are linearly independent. So if you have a 3-dimensional vector space and 3 linearly independent vectors, they form a basis. So it's guaranteed that these fields are a basis. So all the translations, it's actually not hard to compute, but all the translations can just be gotten also from all of these vector fields, right? You think like you see 3 rotating vector fields, but if you take the correct linear combination of them, it will degenerate to, for example, a vector field that looks like this. So of course, now this would be the 4th vector field. It can be constructed as a linear combination of these 3, and you will get out this vector field. It really works. It's guaranteed to work because it is a vector space. Otherwise, this whole concept would not work. We can do the same thing on other manifolds because now we have the same construction. So I didn't mention that these vector fields are called Killing vector fields. So for vector fields that are derivatives of rigid motions, they have a special name after William Killing. They are Killing vector fields. So we can do the same thing now on another manifold, like the sphere that we used in the tutorial. So this is just different basis vector fields on a different manifold, but otherwise it's all the same. So it still does, again, all the rigid motions that are possible on a sphere. In this case, again, there are 3 degrees of freedom. It's just kind of different ones. So here we would like to think about them as 2 translational ones and 1 rotational one. And here it's just 3 rotational ones. If you would do the same in R3, it would be 6 degrees of freedom. So it would be 6 basis functions, 6 basis vector fields also. But so here we have different rotations of the sphere, basically, shown as the derivative of these rotations. And again, we have 3 coefficients, A, B, and C. We just take a linear combination. That's it. We can just represent all the rigid motions. So that means we can do observer computations in R2 with 3 coefficients. We can do it on the sphere with 3 coefficients. The sphere in many ways is much more complicated than a plane, but in this case, it's actually exactly the same. We just use the same construction of a basis. It's just a basis that's a vector field on a sphere. And other than that, there's no difference. So things that we can do with this is basically now we can say, well, now that we know how to model an observer, we can compute derivatives. If you now want to see the derivatives that an observer sees, we have to go a little bit more complicated, but we can start from the time derivative that we had before. So this would be the partial time derivative. We also saw how to compute this in this Lie algebra structure. But in this case, what we can do is we can define what we call the observed time derivative, that one observer whose motion is described by a vector field, in this case it's labeled the vector field u, and we define a new differential operator that has not only this partial derivative, but also the Lie derivative here. And in fact, together this is what's called the time-dependent Lie derivative. So this is what Peter showed and so on, that would be the time-independent Lie derivative for time-dependent vector fields. Now often, of course, we would need the time-dependent one, and it's just adding the partial derivative. So now this would be the partial derivative that's observed, well, the derivative that's observed by some observer. And now we can say, now what does this observer see in terms of a derivative of a velocity field? So the velocity field would be the relative, well, this is the input velocity field, that's the observer motion. We have to take the relative velocity between the two and just apply this differential operator. We just expand it out. And so here this works on any manifold, for any tensor field, in fact. But now we have expanded it for two vector fields. And so we see now there's the covariant derivative that comes up and partial derivatives. So we have now combined together all of these different operators to construct what in the end the observer that is described by the vector field u, what it sees in terms of time derivative. If we would now do the velocity field transformation that I briefly showed before, we would basically switch observers, and after we are done with the switch, this derivative would degenerate back down to this simple one, because the observer seen by itself basically goes to the zero vector field. So it all fits together very nicely. But to define this in general, we can really build on this construction that always works. You might know the material time derivative, which you could write like this. So it's a little bit different than this one, and in fact it does two different things. So the material derivative cannot be used for exactly the same purpose because it ignores lots of things. It ignores, for example, the rotation. So there's no vorticity in the observer motion. So if we have an observer that's not rotating, we could do it with the material time derivative. If we have an observer that's rotating, we have to do it with this one. And if you use this one, everything just works. It will degenerate down for special cases to exactly what we want. There was a nice SIGGRAPH paper this year, co-vector fluids, where the same principle was used to preserve vorticity in fluid simulation. So to switch from the material time derivative to the Lie derivative because it preserves vorticity by itself. So the last examples that I wanted to show is now this actually to use it to transform an input vector field to something that shows features like vortices more clearly. So here now this is space-time, so it's a 2D time-dependent vector field. The vertical axis is time. And what we basically see is that there are some vertical motions where this is a point, it's like the center of a vortex, and then particles would be rotating around the center. So this is the input vector field, this is the output vector field for a specific observer. In this case, this observer minimized this observed time derivative. They are equivalent, but you see the vertical motion here much better than in the other one, which would be even more important for computations that would be observer independent, which comes out here also by itself. We can do that also on the sphere. We have seen before that how we transfer these constructions now from flat space into spaces like the sphere. We use the same operators. In principle, it just works. We just have to know how to evaluate these operators. What we can do there is what maybe we can call feature-centric visualization. So here in this case, there would be a hurricane. And if you look closely, the Earth is actually rotating underneath, but the hurricane is staying in the center. So we can say, instead of usually we have to follow as a hurricane moves, we actually keep the hurricane at the center and we just let the Earth move in the opposite direction, which lets us keep the hurricane in the center. It allows us to compute partial derivatives much more easily and follow what this is doing in place, kind of. Okay, so the last thing I wanted to briefly show is it's just an extension, especially now using this Lie algebra and Lie groups that we just saw. We can really say now we can speak of a family of observers. So physically here just means it's a rigid motion. We can also do other motions, but then they by themselves would not be physical. But we can actually do a framework that has the input vector field here, an arbitrary vector field that's an observer vector field that's not a rigid motion, but then we can extract rigid motions, which basically gives us an infinite family of different observers. And then we can say, now we do this velocity transformation that I showed before, and we just transform into any observer, and we see what this observer would perceive. So that would allow us to do something like this. So this is now, again, a space-time visualization. vortex. If you have another observer, this observer does not clearly see this vortex. Right? If you have a computation that's objective, you would get all of these vortices out by themselves, but if you want to see them in a visualization, it would have lots of benefits to just move the observer exactly following the vortex, and then it would kind of look vertically standing in space-time in some sense. So this concludes this part and also the tutorial. So I think we tried to give you like an overview. I guess it was very fast and hopefully not too confusing, but for sure sometimes a little bit confusing. So I would like to refer you again to the course notes to look at the details. But I think sometimes so one kind of takeaway message maybe is that what might look more complicated mathematically, of course, forces you to learn this mathematical stuff. But after you have done that, I think some things actually simplify. So it's a more complicated notation, it's more complicated concepts, but in the end, the algorithm that comes out is actually much simpler as long as you step kind of over this initial hurdle of getting used to these notations and concepts. Okay, so thank you very much. Let's stop here. So if you have some questions, maybe we can quickly take questions, otherwise we're out of time. But if you have some questions, we are happy to answer. Yes. Yes. So you can reformulate this conservation laws exactly with these operators, yeah. So that was not our main focus, and that's not what we really do. So we would build on computations that already use the conservation laws, but you can reformulate them exactly in the same language. So I would see it more as a differential geometric language to formulate constructs, and you can actually reformulate all these conservation laws like this. Yeah. So there are some books in continuum mechanics that use exactly the same operators. So some of them do what's also usual in visualization often is that it's Cartesian coordinates and so on. So you directly just do the special case for Cartesian coordinates, but you can reformulate all of these just to use these more general constructs, and then they are always just valid immediately from the construction. Yeah. Okay, all right. So let me refer you to the course notes again, and thank you very much for attending. Thank you.